This video will look at getting the vibrational partition function. And just to recall a little bit, we've said that we could get the molecular or the the total partition function, the canonical partition function. The book writes it as capital Z, as these molecular partition functions raised to the nth power over n factorial, where capital N is the number of particles in the system. We've already gotten the translational, that expression for that. We got the rotational, and so now let's turn to the vibrational partition function. And just to recall a little bit of notation on it, we're looking at a diatomic molecule. Could have different molecules A and B with different masses, and we're modeling it as a single vibrator with essentially an effective spring constant or stiffness constant of K. Just to recall, one calculates the reduced mass, which is given by this expression, where Ma is the mass of atom A and Mb is the mass of atom B. One conform the angular frequency, omega naught, which is just the square root of this spring constant divided by the reduced mass. And omega naught is often written as 2 pi times the usual frequency, nu naught, and some books write it one way and some write the other. You should have done the quantum theory on these one-dimensional vibration oscillators. And you either wrote it in this form with h bar, where h bar is h over 2 pi, or h times nu naught. N is the quantum number, vibrational quantum number, and there's this factor of 1/2 here, and n goes 0, 1, 2, 3, etc. That comes out of the quantum theory. And so we just need to use that fact to compute the partition function for an oscillator system. This would be for a molecule. Yeah, so this is a molecular for just the vibration mode. And remember, that's the sum over all the states. In this case, we don't have any degeneracy, and it's e to the minus en over kBt. So our partition function, I substituted in this one here for the energy. And so this sum over states and the sum over energies are exactly the same thing, and there's no degeneracy, or the degeneracy is 1, I guess, in each state. You can use the property of this exponential to break this into two pieces, one that's just minus h nu times n over kBt, and the other one that's h nu naught over 2 kBt. And the reason to do that is because this piece doesn't depend on n, and so it's just a constant that I can pull it outside that sum, which I did here in this next piece. And if you look at that, it kind of motivates, and especially knowing what we've done previously with the rotational, it's convenient to lump some of these parameters so you really just don't have to write so much. And if you look at the units, this h nu naught has units of energy, and kb has units of energy per degree Kelvin. And so the ratio of those two turns out to be the Kelvin will flip over on top, and so this will have units of temperature. And so one gets the vibrational temperature, or the effective temperature of vibration, as related to the stiffness constant effectively, and Boltzmann's constant and Planck's constant. So we'll use that definition. It reduces having to write these three quantities and just writing the one. So I use that up here, and you'll see that you get a theta vibration divided by 2t, and then inside this whole factor is just the vibrational temperature over t. And I'll still have this integer n here. So t over t is dimensionless, and n is just an integer, so a dimensionless quantity in the exponential. And now then we, under certain conditions, can sum this series, under most conditions actually, so long as so long as this theta vibration over T is small, uh, and the in some sense, then one can do this precisely, but it actually works for a wide range of these theta vibrations over temperature. I probably should say, so long as this theta vibration over T is large, we'll be able to sum this series. And so I have this factor. I go ahead and write this out as 1. When n is 1, I just have 1 here. When n is 2, I get a 2. When n is 3, I get a 3, and so on. And this sum here, this infinite sum, I'm just going to call that S. It's everything in between the brackets. And then do a little bit of work on it. And now then, so long as x is small, and that means that this has to be large, so theta vibration over the temperature needs to be a large number, so that drives x being small, then we're on a firm footing. And the sum I can write as, well, if you look at that, it's a theta vibration, which would be x squared, x cubed, and so on. So we get that. And then you can do the usual trick. This x squared, from this point on out, I can factor out an x from each one of these terms. And when I do, I'll get a 1 from here. I'll get an x from this one. I'll get an x squared, x fourth. But this quantity here is just the sum again. So you get this relation that the sum is equal to 1 plus x times the sum. And then that can be solved for x. And solving for x, take this over to this side, to the left side, factor out an s, and then divide through by 1 over 1 minus x. And now then I can put back in what the x was, which is this e to the minus theta vibration over t. And I've got that sum. And that's simply this sum here. And when I plug this back up for the term in square brackets, I get the vibration, molecular vibration partition function. The molecular vibration partition function is this factor times this factor here. It really works over a wide range of temperatures, so even though we started with some assumptions here in terms of the smallness to be able to get convergent series, that's basically what we're trying to do, is make this series here converge. But this infinite sum, even in cases where x is not necessarily small, or this exponential is not necessarily small term, it does really a pretty remarkable job with getting this vibrational partition function. You see it written in several ways, I suppose, and don't be surprised if you see it written in slightly different ways, but this is the form that I'll probably use it in most in terms of the vibrational temperature over 2T, and 1 minus e to the minus theta vibration over T on the bottom. And then, of course, the vibrational temperature is this H nu naught over kV. Well, once we have the partition function, we can start doing some things with it. This is sort of old hat by now. If you've got the vibrational temperature, or vibrational partition function, then I can get the average vibrational energy of one of these oscillators, and that we've represented by the expectation value. And if you remember, that is just kb t squared times the partial derivative of the natural log of the molecular vibration partition function. And I actually simplified this log term a little bit before I took the derivative with respect to t. what did I do here? Oh, I took this as the log of this term minus the log of the log of the numerator minus the log of the denominator. But the log of the numerator, well, those are inverses, and so I just get minus theta vibration over t. And this term I get minus this factor here. And then I can take the derivative of it. So taking the partial derivative, and that's going to be here. I just plug this expression for the log into there and take the derivative. The first term is pretty easy because theta is, and 2 are constants. They can come outside. And then I just get the partial derivative with respect to t, which is minus t squared, but a minus gives me a plus on that. So I get the partial derivative of this first term. Second term's a little bit tougher. The partial derivative of the logarithm, I have to take 1 over its argument, and then the derivative of its argument. The first 1 here, the derivative of that's 0. Derivative of this, I'll get a minus the function times the derivative of the power of that function with respect to t, using the chain rule to get through there. And then again, the partial derivative minus partial derivative of theta divided by t. Theta is just a constant. And so I get, again, a plus a theta vibration over t squared when I take the derivative with respect to t. And a minus becomes a plus. So I get this term and this term here. And you'll notice, having written it out, that I can now plug this for the partial derivative of the log back up here. And to this point, partial derivative with respect to the log is here, so I include that. That's the derivative of that log of z vibration. I get t squareds cancel, which is nice, and I get that the expectation value of a single particle is theta vibration over 2 plus theta vibration e to the minus theta vibration over t, 1 minus e to the minus theta vibration over t. If I have a system of n particles, then if I multiply all of those in, I can get the expectation value of the energy, which would be the total energy in our case. And as usual, n times kb we can write as the number of moles, now n times the ideal gas constant. And we can factor out this theta vibration. Sometimes you see it factored out, sometimes not. So that would be for a system of n, where n is a very large number of one-dimensional oscillators. Well, you can calculate other quantities, entropy, etc., enthalpy, as the case may be, and I won't belabor that and just be satisfied with the most important one, which is the internal energy in this case.